Good day, folks. I'd like to talk to you about this, the topic here. It's a topic of research I've been working on. I was going to build it an experiment, but the person who was donating some of the parts to help me got some illness in the family, so with that said, could no longer help me out, understandably, funds-wise, so some of the parts I needed, so it went on hold for a while. So I was going to wait until I actually had something more workable to show here to prevent basically the trolling of the idea here beforehand, but since I'm running out of parts, I will make the presentation anyways. And perhaps if anyone wants to help here, they want to help out, they could maybe get a hold of me and they could maybe donate some of the parts that I needed here to continue this. But so to start, let's talk about this here in more details here. A nonlinear ferroelectric capacitor, as the title states here. It's got barium ferrite and ceramic dielectric. It's a mixture you would make, and basically a nonlinear ferroelectric capacitor. It's a device that exhibits a nonlinear relationship with the between the electric field and the polarization of the materials. In simpler terms, basically, as the voltage across the ferroelectric capacitor increases here, the amount of electric charge it can store does not increase linearly like a normal capacitor. So it introduces interesting. It's primarily due to the characteristics of the ferroelectric material, like as I was saying here, which has a spontaneous polarization that can be reoriented by the application of an external electric field. This non-linearity is often represented by a hysteresis loop in the charge voltage, the QV in other words, where the amount of charge stored on the capacitor depends not only on the present value of the electric field, but also on the history of its electric field. So it's got a bit of a memory. The area within the hysteresis loop is related to the energy lost in the process of charging and discharging the capacitor. Potential applications of nonlinear ferroelectric capacitors I have listed here. So we're going to start with energy storage here. They can be used in energy storage applications where high density energy storage is required. That's due to the ferroelectric materials can store more energy than conventional dielectrics of the same size. That's an advantage right there. Power electronics and power electronics basically, they can be used to create filters, oscillators for example, other components that require tunable capacitors for example. So very handy for that. It could respond to changes to voltage very quickly. It makes them useful for high frequency applications as well. We have the sensing applications here. Nonlinear capacitors can be utilized in sensing applications because of its, especially in the environment where the nonlinear response would not be sufficient. How can I word this? For instance, ferroelectric capacitors could be used as pressure sensors. Since the capacitance will change non-linearly with the pressure, for example, because of the piezoelectric effect. There's memory devices as well. The hysteresis loop of the ferroelectric capacitor here, it makes them ideal for non-vulnerable memory storage, basically. So computing applications. The two states of polarization can represent binary data, basically, is what I'm getting at. Zeros and ones. And the data is retained without power, which is pretty cool, really. It could be used for energy harvesting. It could be used for this as well. Many devices to collect and store energy from the environment, like we're trying to do here, which is good for that. Kinetic energy could be converted, even vibrational energy, because of the ability to convert the mechanical stress into an electrical form of energy as well. So there's the frequency tuning as well. The ferroelectric capacitors can be employed, for example, in tunable microwave and radio, even high frequency. RF applications, RF devices. The capacitance of these components can be dynamically adjusted by applying, for example, different voltages, which in turn changes the resonance of the frequency, so frequency tuning. And of course, there's the quantum computing. There's an interest in using ferroelectric capacitors in superconducting circuits, for example, for quantum computing applications. That would be due to their potential to act as quantum bits, basically. Qubits is the name for it. Negative capacitance as well. Ferroelectric capacitors could exhibit negative capacitance behaviors. This could be useful in making low power semiconductors, for example, and could be the basis for future low power computing technology as well. So it couples with the quantum computing here. So in sum, nonlinear ferroelectric capacitors here, their components, range of applications here across various fields, as you can see here. This is just a few I thought of, there's probably more, particularly where unique characteristics such as tunability, for example, high energy densities, or nonlinear responses in general where that's desirable. The technology obviously continues to be a subject of extensive research, but there's not much out there. It promises to unlock even more applications as understandings and the materials science advances. Tom Bearden talked about this a lot. Without getting into the details, he said that it was basically all private contracts with the military, and regular users didn't have access to buying commercially made nonlinear ferroelectric capacitors. So with that said, let's move on here. All right, folks, here are some details here. So we start with the piezoelectric plates here. These are usually made of materials like quartz or certain ceramics that generate a voltage when mechanical stress is applied, and vice versa. They inherently have ferroelectric properties as well, so good combo. And the barium ferrite powder here, when processed into a ceramic form here, it has ferroelectric properties, and it can act as a dielectric in capacitors here. I've got a rough diagram here for constructing it here. So there's your barium layer your piezo plates in black, and the electrodes in orange. So first you got to prepare the barium ferrite ceramic layer. The powder would need to be compacted and centered to produce a very thin ceramic plate here. You'd want to place the barium ferrite plate between the two piezoelectric plates here, as I show in the picture here. This arrangement means the outer layers are piezoelectric, while the core layer is barium ferrite dielectric layer. The electrodes will need to be attached, obviously, to the external sides of the piezo plates here for proper operation to allow for the electrical connection and connectivity here to the capacitor. Plate sizes and thickness of dielectric will determine the starting neutral parameters of the capacitor here without excitement, along with the nonlinear ferroelectric properties of this device here. Operation of all of this, when the voltage is applied across the electrodes, not only will the barium ferrite layer respond due to its ferroelectric nature, but the piezoelectric plates will also undergo slight mechanical deformation. This dual reaction can result in interesting nonlinear behaviors, obviously here what we're looking for. If this assembly is mechanically stressed, for example, by vibrations or compression, the piezoelectric plates will generate a voltage as well, potentially modulating the voltage across the barium ferrite ceramic layer here, which is very interesting, like Tom Bearden was talking about. The electric field manipulation of the ferroelectric material within the capacitor, it'll have an electric field applied to it, which can alter its polarization. Nonlinear response, ferroelectric materials, they have a nonlinear response to the applied electric field that we're putting in there, which can be exploited for various purposes, as Tom Bearden was saying. Send it the right pulse, you get a pulse back, including frequency doubling, generation of higher harmonics, very good energy storage, advanced energy storage, and advanced transfer in a nonlinear manner. In some applications, the pulsing of an electric signal is used to manipulate the state of the ferroelectric material to achieve the desired electrical outcome here. So there's multiple applications, but all good ones. Inclusion to understand the need for a specific combination of materials in a nonlinear ferroelectric capacitor. Let's delve into the properties that each component brings to the device in more details here. For all of this to work, the piezoelectric plates in this example, the piezoelectric materials, as I've said before, exhibit a direct piezoelectric effect, which means that they'll generate an electrical charge here when mechanically stressed, as I've stated before. They can change shape as well when an electric field is applied. The reverse piezoelectric effect is valid here as well. These materials are also ferroelectric, meaning they have a spontaneous polarization that can be reoriented by the application of an electric field to the input here. The nonlinear properties of piezoelectric plates, it can be very critical for applications where the dielectric constant of the material changes with the applied electric field. It affects the capacitance of the components. The barium ferrite dielectric here uses the barium ferrite, and it's a type of ferromagnetic material. It can also exhibit a ferroelectric property depending on its crystal structure, for example, and composition. So we need to get the right materials. Could be tricky. As a dielectric and a capacitor, basically, it can contribute to the non-linearity in the devices where the response. The ferroelectric materials are known for their ability to have their electrical polarizations switched by an external electric field. So very interesting. And they also exhibit a nonlinear relationship between the applied electric field and the induced polarization. So the reason you'd want to have both the piezoelectric plates and the barium ferrite layer, the dielectric, together in a nonlinear ferroelectric capacitor, basically, it could be very many reasons. Enhance nonlinearity. The combination, it's aimed at enhancing this effect, the nonlinear characteristics of the capacitor. So we use everything we can, for all the systems we can. The piezoelectric plates, it contributes to the mechanical electrical energy conversions, while the barium ferrite can add to the electrical nonlinearity due to its ferroelectric properties as well. So lots going on here. Multifunctionality is what I'm getting at. By using both materials, we can come up with something potentially that broadens the operational range of the capacitor as well. So it could be useful in even more applications. So you can understand why the military wants to keep this juicy for themselves. For instance, the piezoelectric component might be useful in frequency-specific applications. It would help with that. While the barium ferrite, that would be more for the hysteresis, which would cause the polarization switching. Beardini talked a lot about this with the barium ferrite. It's got memory, folks. So some applications, the use of piezoelectric plates might be to introduce a controllable mechanical aspect to an otherwise purely electrical component. So again, using multiple systems together, this could be useful in resonance circuits. I've said it before. Situations where mechanical feedback, for example, true vibrations, sensors, shape changes, this could all be used to control and contribute to the electrical characteristics of this capacitor. Customizable properties makes it awesome. Different materials, for example, could be used to tune the capacitor to specific requirements. For instance, the barium ferrite might provide the desired ferroelectric hysteresis loop that we need for a certain circuit, while the piezoelectric plates might be selected for their specific response to an electric specific field or a mechanical feedback. So wow, back into the Beardini systems and everything we're working with, I know this is a lot to swallow, folks. It's really digging deep, and again, I was going to do all of this. Right now, the parts, actually what I do have is right over here. I ended up getting one of the powders for the mix. This is, I didn't specify it, but I was going to use this for my electrodes, which is copper oxide. Also has semiconductive properties. So again, I ran out of parts to finish this, and I hope that I sparked an interest. And if anyone wants to donate the rest of what I need, I never got the barium ferrite, I never got the piezoelectric plates, unfortunately, and no one's fault, obviously, but that's just the way it is. And I'm also testing a new microphone, so hopefully this is going to fix the quality issues with the audio as well, so we'll see after the recording. And with that said, like always, thank you for watching, folks, and thanks for your support, and we'll see you in the comments section. Have yourselves a great day.